So this is lecture number 8 in the series on control systems 2. And in the previous lecture, we actually discussed how to transform a state variable model into a single flow graph and vice versa. And now what we'll be doing is in this session and coming sessions rather, we'll be discussing state space to transfer function and transfer function to state space uh, approach. How to derive a transfer function from a state space model and how to derive a state space model from a transfer function. We'll be looking at this in the next few sessions, in the next 2 to 3 lectures. Uh, but today we'll start with first the state space to transfer function, how to derive a transfer function model from a state space model. Transfer function can be derived easily from a state space model, and this we'll try to derive the equation for this for derivation of transfer function from a state space model, and this will start with the state space model, defining the state space model. As we have already know, the state space model of a system can be defined as x dot equal to x plus bu and y is equal to cx plus du. So these two sets of equations, as we know, represent the state space model of a system. So let's number these equations as 1 and 2. To obtain, now these two equations are in time domain that we already understand. The state space model, these are defined in time domain. So to obtain a transfer function model, we know that a transfer function model is defined in S domain. So what we can do is we can actually apply the Laplace transform to these equations, find out the transfer function model. So applying the Laplace transform to equation number 1. Laplace of x dot t is equal to uh, Laplace of ax t plus b u of t. Fine. So Laplace of x dot, Laplace of d by dx of d by dt of xt. We know that Laplace of a differential is given by s times x of s minus x0 is equal to lap a is a constant here, so Laplace of xt will be simply x of s plus b is a constant here, Laplace of ut will be u of s. So this is the Laplace. Now we know when we are trying to derive a transfer function of a system, we assume the initial conditions are 0. So that means x dot 0 will be substituted to 0. So in other words, we can say s times x of s is equal to a x of s plus b u of s. So from here, s xs s times x of s minus a times x of s is equal to b times u of s, which implies si minus a x of s is equal to b u of s. So when we take x of s common, fine, since x a, these are all matrices, so instead of having s into 1, we'll be having s into I, an identity matrix, where identity matrix basically represents the 1 in linear algebra, one in we can say in simple numerical representation. We can replace 1 by an identity matrix while representing a matrix algebra. Uh, what we are going to be doing is pre-multiply both sides by Si minus A inverse. So Si minus A inverse into Si minus A, pre-multiply x of S is equal to Si minus A inverse B U of S. Since matrix algebra is not commutative, we need to keep in mind while we are actually trying, as far as this step is concerned, we took x of S common, but it has to be post common, it cannot be pre-common to Si minus A. And similarly here, we are pre-multiplying by Si minus A inverse. So Si minus A inverse into Si minus A is identity matrix. So identity matrix into any matrix is that matrix itself. So this will be x of S is equal to Si minus A inverse B U of S. So this is your equation number 3. Now applying Laplace transform to equation number 2. Equation number 2 was y is equal to cx plus du. So applying Laplace transform to that, Laplace of y of t is equal to Laplace of c xt plus d ut. Laplace of y of t is y of s is equal to c x of s plus d u of s. Fine. So substitute equation 3 in equation 4. Equation 3 is actually x of s is equal to this whole as I say inverse b u of s. So we get y of s is equal to c. Instead of x of s, we will be having Si minus A inverse B U of S plus D U of S. Right? So in other words, if we take y U of S common on both sides, y of S divided by U of S will be equal to C Si minus A inverse B plus D, where Si minus A inverse is actually an inverse matrix, and we know that inverse matrix can be determined by finding out adjoint of Si minus A divided by determinant of Si minus A. So that means y of s divided by u of s is equal to C adjoint of Si minus A B plus D divided by Si minus A. We know that the denominator of a transfer function is basically the characteristic equation. So characteristic equation can be directly found out from a state space model by finding out the determinant of Si minus A equal to, by putting this determinant equal to 0. So the characteristic equation basically gives the poles, the roots of the characteristic equation give the poles. So in other words, the eigenvalues of A matrix are nothing but the poles of a transfer function. Fine. So when we define stability, we say the poles of the transfer function should be negative. We can directly relate it to a state space model and say that eigenvalues of matrix A should be negative. So this is how we derive the transfer function from a state space model by using this equation y of s, or you can simply write g of s is equal to c Si minus A inverse B plus D. This is your equation. So using this equation, we can derive the transfer function of any system that's whose state space model is given. So we'll be doing an example. So let's find the transfer function of the following state space model. Zero 1 minus x minus 2 x1 x2 plus 0 1 u. Y is equal to 3 0 x1 x2. So we know now transfer function is given by the equation C as I minus A inverse B plus D. So first of all, we need to find out as I minus A inverse. Fine. So what will Si minus A inverse be? It will be equal to S into I. The order of I will be the order of A matrix. Since A is 2 cross 2, I will also be 2 cross 2 matrix. 1 0 0 1 minus A 0 1 minus 6 minus 2, the inverse of this. So this means basically S minus 0 minus 1 plus 6 S plus 2. We need to find out the inverse of this matrix. So Si minus A inverse is equal to S6 minus 1 S plus 2 inverse, which gives us adjoint of S divided by the determinant of S. Determinant of this matrix is S into S plus 2 plus 6, that is S square plus 2S plus 6, and the adjoint of this matrix is basically the transpose of the cofactors of each element. Cofactor of S plus 2 is S plus 2. Cofactor of minus 1 is 6. The transpose of it will be here minus 1 raised power the power of the elements 1. So this will be the inverse of this matrix that we can calculate using the formula adjoint divided by the determinant of the matrix. So G of S now will be equal to C Si minus A inverse. C matrix here is 3 0, B matrix here is 0 1. C is 3 0. C Si minus A inverse. Si minus A inverse is S square plus 2S plus 6 times S plus 2 minus 6 1 S. C Si minus A inverse. B matrix is 0 1 plus D. D here is actually 0. So multiply, this is 1 by S square plus 2S plus 6. Since it is a constant, we can take it out. So we can either multiply this matrix first. On multiplication of these two matrices, S plus 2 into 0 is 0 1 minus 6 0 S, it will come out to be 1 S. So again, multiplying 3 into 1 plus 0 into S, that means 3. So this will be 3 divided by S square plus 2S plus 6. Fine. So this is your answer. This is G of S, the transfer function of the state space model that we obtained actually is S square plus 2S plus 6. Fine. So we can now actually, if we want to find out the poles of this equation, we can substitute s square plus 2s plus 6 equal to 0 and see what will be the location of the poles. Right? So this is about state space to transfer function approach. Second, we have to study transfer function to state space model. How we can obtain a state space model from a transfer function. So this process is more of a graphical approach, block diagram approach rather than simple mathematics. We'll be using block diagram algebra, block diagram reduction methods of control systems that we have studied already to find out the transfer function, to find out the state space models from the transfer function of the system. Now we know that we have already studied that the state space model of any system is not unique. So a system can have a number of state space models. You can have a single state. You can have different forms of state space models. In short, if we have any matrix, what else? You already are aware about this fact. If we have any matrix, we can use any matrix algebra to transform it into another matrix having the same properties but different in but different in appearance. Fine. So we know that we can add one column to another, or we can add rows with each other. Fine. We can do this kind of transformation to matrices where we are adding row number 2 to row number 1, or we can add column number 2 to column number 1, or we can add column number 1 to column number 2, or we can do simply scalar multiplication, scalar divisions. So in short, all these matrices obtained from transformation of or any all these matrices obtained from the original parent matrix by various matrix algebra transformations render a matrix basically. These all matrices will have the same property as the original matrix, but they will be different in appearance. So one state, so for any system in a similar fashion, we can obtain a number of state space models, and there are three important state space appearances that we'll be studying, that we'll be deriving. These are known as the companion forms or the canonical forms. So these three state space models that we'll be obtaining are referred to as the first companion form, the second companion form, and thirdly the Jordan canonical form. So all these state space models have this different appearances, but they actually represent the same system. They will be representing the same system, having the same properties as that of the original matrix, and but will be different in appearance. Right? So we'll be studying three different forms, three useful forms rather that are going to be helping us in reducing the state space modeling approach, making it easy for us to do the analysis of state space models. So that will be covered in the next lecture. That's all for this